To see how a DNS cache poisoning attack works, consider a network where a stub resolver issues a query to its recursive resolver, and the recursive resolver in turn sends that A record query to the start of authority for that domain. Now, in an ideal world, the authoritative name server for that domain would reply with the correct IP address. If an attacker guesses that a recursive resolver might eventually need to issue a query for, say, google.com, the attacker can simply reply with multiple specially crafted replies, each with different IDs. Although this query has some query ID, the attacker doesn't need to see that query because the attacker can simply flood the recursive resolver with a bunch of bogus replies, and one of them, in this case the response with ID 3, will match. As long as this bogus response reaches the recursive resolver before the legitimate response does, the recursive resolver will accept this bogus message, and worse, it caches the bogus message. And DNS unfortunately has no way to expunge a message once it has been cached. So now this recursive resolver will continue to send bogus A-record responses for any query for this particular domain name until that entry expires from the cache. Now there are several defenses against DNS cache poisoning, and we've already seen one, which is the query ID. But of course, the query ID can be guessed. The next defense is to randomize the ID. So rather than having a resolver send queries where the IDs increment in sequence, the resolver can pick a random ID. This makes the ID tougher to guess, but still, the query ID is only 16 bits, which still makes it possible for an attacker to flood the recursive resolver with many possible responses, and it's likely that with relatively few responses, one of these bogus responses will match the ID for the real query. Due to the birthday paradox, the success probability for achieving a collision between the query ID of the query and of the response actually only requires sending hundreds of replies, not a complete 32,000. Due to the birthday paradox, the probability that such an attack will succeed using only a few hundreds of replies is relatively close to 1. The attacker does not need to send replies with all 2 to the 16th possible IDs. The success of a DNS cache poisoning attack not only depends on the ability to reply to a query with the correct matching ID, but it also depends on winning this race. That is, the attacker must reply to that query before the legitimate authoritative name server replies. If the bad guy or the attacker loses the race, then the attacker has to wait for that correct cached entry to expire before trying again. However, the attacker can generate his own DNS query. For example, he could query 1.google.com, 2.google.com, and so forth. Each one of these bogus queries will generate a new race, and eventually the attacker will win one of these races for an A-record query. But who cares? Nobody necessarily cares to own 1.google.com or google.com. The attacker really wants to own the entire zone. Well, the trick here is that instead of just simply responding with A records in the bogus replies, the attacker can also respond with NS records for the entire zone of google.com. So by creating one of these races using an A record query and then responding not only with the A record response but also with the authoritative of the NS record for the entire zone, the attacker can in fact own the entire zone. This idea of generating a stream of A record queries to generate a bunch of races and then stuffing the A record responses for each of these with a bogus authoritative NS record for the entire zone is what's called the Kaminsky attack, after Dan Kaminsky, who discovered the attack. The defenses of picking a query ID and randomizing the ID help, but remember the randomization is only 16 bits. So let's think about other possible defenses.